start recording. Okay, so the next talk will be about sets with rational linear parents by Malabika Pramanik. So Malabika, whenever you want, the audience is yours.
Okay. Hi, everyone. Thanks very much to the organizers for the opportunity to be here today. What I'm going to do is report on some ongoing work with Yu Liang about sets avoiding certain rational linear patterns. So I'm just going to write here so that I can slow myself down. So I'll focus only on reporting some of the main results instead of going into the guts of the proof. Okay, so I'll get started. Okay. All right. So the main thing that we are going to be concerned with is something called a translation invariant linear equation with integer coefficients. So what exactly is that? So let me write that down. Everybody can still see and hear me, see this and hear me, right?
Yes, everything is
Thank
okay.
you. Okay. So what is a translation invariant linear equation? With rational coefficients. So I'm going to always refer to this as objects of this form, a1x1 plus a2x2 plus etc. all the way up to ap xp equals b1y1 plus b2y2 plus bq yq. So here the coefficients a1, a2, ap and b1, b2, bq, these are positive integers, and x and y, the vector x with entries x1 through xp and y1 to yq. So these are the unknowns. And without loss of generality, we can assume that p is larger than or equal to q. Why? What do I mean by translation invariant? Well, this is really a condition that we will always impose, which is that the sum of the a's, a1 through ap, equals the sum of the b's, b1 through bq. And I'll explain in a moment why this condition is a good one to have. Well, what this implies is that if x comma y is a solution to this equation star, and I will always refer to this equation star throughout my talk, that means that if xy is a solution, so if xy is a solution of star, so is xy plus t for any t in the reals. Okay, so hence the name translation invariant. All right, so we'll be interested in determining the solvability or not of such an equation. So here's the definition. We are going to say that a solution x comma y is non-trivial if all the entries x1 through xp, y1 through yq are all distinct. Okay. Now, clearly, we are not trying to solve this equation in the reals. Otherwise, there wouldn't be much to say. So we'll talk about, before I go any further, how about an example? Probably the best known example in this class, which is x1 plus x2 equals 2y1, and non-trivial solutions of this equation signal the existence of three-term arithmetic progression with a non-zero common difference. Okay. Now, we will be looking for solutions in certain sets. So one more definition to go. So suppose that we have a set E, subset of R. We are going to say that E contains a non-trivial solution of star if there exists xy satisfying that equation, obviously, such that each one of these entries, so this belongs to, each entry belongs to E. So this belongs to E to the power of P plus Q. And if there no such solution exists, if no such solution exists, we say that E avoids star. Okay. All right. So with that in mind, I'm going to sort of pose the following question, which has been studied quite a lot. So here's a question. How large can a set E be while still avoiding star, an equation of the form star? Okay, so not surprisingly, this is not a very well formulated question, and the answer depends on what large means. Okay, so just to give you a flavor of the results that are known, there is a result from 2014 due to Andreas Mathe, which says that there exists a rationally independent set E of in R of full Hausdorff dimension. And of course, Rationally independent means that you cannot have any kind of non-trivial linear relationship among the elements of capital E with rational coefficients. In particular, what this means is that you cannot find any non-trivial solution of any equation of the form star. So and keep skipping the word non-trivial, so but that's always implicit. Okay. Now, there are positive results too, and one of the positive results that's joint work with Isabella Laba from a while ago, dating back to 2008 or 2009, was, well, even though there are large sets without rational dependencies, with some other formulation of largeness, we do have a positive result. So let's try to give a easily statable version of that result. Okay. If So if E supports a probability measure such that two properties are satisfied, one is a ball condition that the probability measure mu assigns to each ball a mass that's bounded by C1 times the radius to the alpha and obeys a Fourier decay condition. To the power of with an exponent of decay beta, and then provide then E contains a non-trivial three-term AP, provided alpha is sufficiently close to 1. Okay. All right. So this seemed to suggest that if you had some extraneous condition other than the condition for Hausdorff dimensionality, maybe what one ought to be able to find an arithmetic progression in such sets. Well, at least that's what I thought at the time until Pablo proved us wrong. So what his results say, so he said that even though, so these results are consistent with a conjecture that perhaps sets of high Fourier dimension ought to contain three-term arithmetic progressions, but that intuition is false. In fact, there exists a set full Fourier dimension, and I'll remind you in a moment what that is, although I know that there are many in the audience who know this, such that E avoids all three APs. So just to remind you, if E is a Borel set, the definition of the Fourier dimension of a set is that it's the supremum of all exponents beta, and this is between 0 and 1 because this E is on the real line, such that E supports a probability measure nu, such that nu hat has a certain rate of decay at infinity. Okay, all right. So this result was slightly confusing because it seemed to apparently contradict this meta principle that somehow is part of the folklore and has many different manifestations. So, what is this meta principle? So, it seems to be that a set of large Fourier dimension ought to enjoy more arithmetic structure or more arithmetic properties compared to a general set of large Hausdorff dimension. And this seems to contradict this. Certainly, where identification of three APs go, Hausdorff dimension and Fourier dimension, there doesn't seem to be any perceptible difference. So this we were confused about, and in this work with Yu Liang, what we were trying to do is try to find a way to understand how Fourier dimensionality and Hausdorff dimensionality can be understood in the context of existence of rational linear patterns. So I'll state our main results now. Okay, so suppose that script f um, be the collection of all translation invariant rational equations of the following form. So I'm going to call it type 1Q. So let me write this of type, and by that what I mean is it's of the form, or maybe I should have written P comma 1, I'm sorry. So this is of the form A1 x1 plus A2 x2 plus AP xp equals y, and the sum of these a's equal 1, and each aj is a positive rational. Okay. Then, so our results sort of come in three categories. Part one is that this is exactly this is a generalization of what Pablo observed, that for any finite subcollection f naught, script f naught, of f, there exists a set E naught of Fourier dimension 1 avoiding all the equation star in f naught. So that's part one. Part two is a little bit, not a strengthening, but to say that a similar result can be obtained for a certain countably infinite subcollection of script f as well. So there exists a countably infinite f star contained in f and E star subset of 0, 1, compact, etc., etc., also of full Fourier dimension, avoiding all double star in F star. And the third part is a counterpoint, which sort of really distinguishes how Hausdorff dimension and Fourier dimension stand apart from each other. The whole moral of the story is you can avoid certain things, but you can't avoid everything if you are in a set of large Fourier dimension. So for any E, subset of 0, 1, with whose dimension, Fourier dimension, is larger than 2 over p plus 1, there exists some equation in script F such that E contains a non-trivial solution of double star. And in fact, there exist many such double stars, and we can sort of put some quantitative statement how many there are as well. Okay, so this is the one that ought to be compared with the result of, so this is where, so one corollary of this is that there cannot be any rationally independent set of positive Fourier dimension. In particular, Mathe's set has Fourier dimension 0. Because the moment you choose a set of positive Fourier dimension, that dimension is going to exceed 2 over p plus 1 for some large p. And the moment it does, that the positive Fourier dimensionality is going to force the set to contain a non-trivial solution of some equation in script F. Okay. All right. So I think I have about maybe 5 minutes left. So what I'll try to do is just give a very quick overview of the results. A few things that I haven't mentioned is there had been prior work in a related direction in the continuum due to Corner. And in the discrete setting, this is a very well studied area with contributions over a long period of time by many people. Certainly Berendt, Roth, Zemeredi, Ruja, these are names that come to mind. Okay, so what about an idea of the proof? And and of course, the proof of 1 and 2 are necessarily somewhat different from the proof of 3. And for proof of 1 and 2, we took Pablo's idea as the core. So I'll only focus on part 3. All right, so the idea is the following. I'm going to first give a non-proof, but hopefully you will see how to make this non-proof into an honest to goodness proof if we had sufficient time. So we start with this identity that if mu is a probability measure, so we have E, and we have a probability measure mu supported on E. And we are going to proceed by contradiction and assume that E does not contain, the Fourier dimension of E is larger than 2 over p plus 1, but E does not contain any non-trivial solution of any double star in F. So this is by contradiction. and assume no solution. Okay, all right. So now what do? We start with this probability measure that is given to us with the Fourier decay. So with Fourier decay almost 2 over p plus 1. Okay. And we are going to write this, take 3 copies of it, and you will see in a moment why. And by the way, I'm just giving a prototype proof, and this proof is going to work for p equal to 2 and with some very minor modifications for a general p. Okay, so the fact that p is 2 dictates that I'm taking p plus 1, which is 3 copies. All right, so by permutation invariance, I can write it again as the same integral, except this time with a certain ordering, namely that x is less than z and that's less than y. Okay. And at this point, I'm going to make a change of variable. So we are going to replace the variable z by t, and t is going to belong to 0, 1. And because z is intermediate between x and y, we can write z as tx plus 1 minus t y. So all we do is make a change of variable. So this is going to be d mu x, d mu y, and d mu of tx plus 1 minus ty. And if you sort of pretend for a moment that these are functions, they are not, but you know how to turn them into functions by convolving with an approximation to the identity, then you are going to get a continuous function, absolute value of x minus y as a Jacobian. Okay, now what do we do with this object? So the thing to notice is that 2 observations to check that this inner integral depends on t, and the dependence on t is continuous. So this needs a proof. And second, if you have a continuous function on t, so I'm going to write this in a cleaner way so that you can, if let's say write it as functions, so this would be a mu epsilon x, a mu epsilon y, and then a mu epsilon of tx plus 1 minus t y. And then we have a dx dy as the inner integral, and on the outside we have a dt. And what I'm claiming is that this function, this inner integral f of t, is continuous in t. So t to f of t is a continuous mapping. Moreover, if t is rational in 0, 1, ft is 0. Why? This goes back to our proof by contradiction. We had assumed no solution. In fact, the fact that there is no solution means that this object, which picks up exactly the solutions, has to vanish. If it were non-zero, that would mean there exists some solution. And now you see where we are going with this. This would then say that f of t has to be identically 0, which means that this side is 0, giving you something along clearly a contradiction, 1 equal to 0. Okay, so this is a very, very sketchy proof, but hopefully you can see how to sort of make this rigorous. A lot of, I don't know, dominated convergence theorem, this, that, and the other. And this proof also extends to all P, similar methods. I think I'll stop with that. We have some follow-up progress to report, but I think I'm almost out of time. Thank you very much.
Okay, thank you very much, Malabika, for a wonderful talk. You can imagine our claps here because everyone is muted. But okay, now we have some time, some minutes for questions. So if you have any questions, anyone?
Well, I have one, but it's very
Okay.
stupid. Because in this last integral that you wrote, Malabika,
Yes.
I understood the part of the mu epsilon, but I didn't understand where the x minus y went.
Oh yeah, it didn't go anywhere. I'm sorry. So this where this went, I forgot to write it. So there is an
Okay,
x minus y.
okay, then
and
it's
you
okay.
see, this is a measure lambda acting on this function f, which is x minus y.
Yeah, exactly.
Right.
Okay, sorry. That's why I thought all of a sudden it was constant and I couldn't see that.
I'm sorry. So this lambda sub t is a measure. And if this measure is the zero measure, which it is by our assumption, then this measure acting on the function, in particular, the absolute value of x minus y function, will give you 0. My bad.
Yeah.
Thank
you. Okay. Sorry.
Any other question?
I have a question.
Please, Asita, go.
Hi, Malabika. Thanks for the talk. Very nice talk. I was just wondering if this the bound from below in the item 3 when you said it
Okay, let me
free
see.
dimension is larger. Yeah, when the free dimension is is that sure? Can I go a little bit down, or what is the hope for the other?
Question. So all I do know is that this is what we need for our proof. And our proof, this bound really ties with the absolute convergence of certain multilinear integrals that count these patterns. Now, it's quite possible that even if those integrals were not absolutely convergent, one could still count the existence of these rational patterns in some other way. And there has been other contexts where this has been done. So maybe the best I can say is that right now this is an artifact of our proof. I don't know if this is truly sure.
Thank you.
Okay.
Malabika.
Any other question? Here, Christina, please.
I have in the proof, or in the sketch of the proof, maybe you said it. By the way, beautiful talk. Where does the 2/3 appear?
Where does the 2/3 appear?
Yeah, because you.
Yes,
yeah.
yes, perfect. Thank you. So, this 2 over p plus 1 is the 2/3, right?
Yes. So,
excellent.
But it's supposed to give the contradiction, no?
That's right. So let me move up and show you. So you see the 2/3 is kind of hiding in this integral expression. Okay.
Okay.
You see, we need to make sure that these integrals that we are throwing around make sense, and they are convergent integrals. If you recast this integral in terms of its Fourier transform, you are going to get something, forgetting that absolute value of x minus y for a moment, you are going to get something like bounded above by this.
Okay.
And you see, that's where, so I know that this is big O, this is big O of mod z to the power of minus beta over 2 for each one. So power of 3 would contribute a 3 beta over 2, and we would need 3 beta over 2 to be larger than 1 to make this integral finite. Otherwise, if we don't have this, then we don't know how to attach a meaning to these integrals that we are writing. That's where the 2/3 is hiding.
Thank you.
Excellent. So I think we should thank Malabika again for a wonderful presentation. So thank you very much. And if you have any other questions, maybe we can use the forum to that end.